can declare a sequence to be ascending or descending. You can specify a step increment for how the values progress, and you can also specify whether it cycles through its range, and so on and so forth. So sequence objects within the database were introduced in Oracle version 6. So they've been around for a very long time. So before we had sequence objects in Oracle, if you had a user or an application that required such a unique number generator, you had to find workarounds in the application. And this invariably involves some kind of serialization, either at the transaction level, sometimes even higher, like getting a lock at the application level. And of course, a higher level of serialization will guarantee, perfect ordering as far as the application is concerned. But it turns out that most applications aren't looking for this kind of perfect ordering. They're simply looking for a unique number generator and nothing more. And so for this common generic use case, having a sequence database object makes a lot of sense, because you can have low-level serialization built into the database object, and that helps to scale much better. So it must be pointed out that sequence objects don't give certain guarantees, which surprisingly many people seem to just expect, given that it's a unique number generator. The first is that it does not guarantee commit time ordering. Even ordered sequences, which by definition are supposed to return values ordered, cannot provide this guarantee. And it's easy to see why. Like, so if you have a bunch of sessions that are all accessing the same sequence, they all get next vals or the sequence values according to some order, but depending on the order in which they commit the transactions, the values can be unordered between the sessions. Another guarantee that sequence objects don't provide is gapless values. This is another thing that sometimes users generally ask why they see gaps. So in fact, if you go down to the lowest level details, from the sequence object, you actually get values that are gapless. However, the user experience may not reflect this. And this is because of various reasons. Like if you just abort a transaction, if you have session or instance failures, of course, you're going to lose values. But even without failures, if you're in a multi-user environment where you have multiple users sharing the same sequence, the users may see values with perceived gaps, but these aren't true gaps, because what you see as a gap is basically values that were returned to other users. And of course, all of this looks worse in a multi-instance environment, because you have not only do you have multiple instances, but you have also multiple sessions that are all accessing the same sequence. So what is a guarantee that sequences can give? The primary guarantee that you get is that every value is unique. And once a value is given out, it will never be repeated. And even this comes with certain caveats, because you can use DDLs to alter like the min value, max value, and force a sequence to duplicate values. But in the absence of a DDL, you're guaranteed unique values. Okay. The syntax is something that you can easily find online, so I'll try to spend less time on it. It's fairly simple. You can create a sequence with a number of attributes. The common ones that you would use would be min value, max value to define the bounds of the sequence. The increment gives you the step size. The size of the increment gives you the direction. So if you have a positive increment, say n, it means that every value is greater than the previous value by n. If you have your increment be a negative number minus n, then every value is going to be less than the previous one by n. The alter sequence DDL is very similar to the create sequence. It pretty much takes about the same attributes as the create sequence DDL. One exception is the restart. So all of the attributes that are shown in red are the ones that we're going to look at in slightly more detail in the following slides. So they're either like less used, like keep, session, etc., or they're really important, like the cache and order attributes, because they're on the critical path of performance. So let's say you created a sequence already. Now the operations on the sequence are very simple and straightforward. There's only two things you can do. You can either get the next val, which is the next value from the sequence, or you can get cur val, which is the last value that was already given out. Okay. So how do applications typically use database sequences? One common use is to generate automatic primary keys that feed into a table column. Now, these columns typically have an index and some constraints on them. A second use case could be, to generate automatic primary keys, but with the constraint of having ordering on them. One example is if you're using a sequence to feed into the reservation ID column of some kind of reservation system, it's easy to see why you would want reservation IDs that come later to have greater values. Finally, you might have an application that just simply wants a unique number that's not going to feed into a table. Of course, this sounds less common, but it's not unheard of. So the curval and nextval that we saw on the previous slide can be used directly in SQL Plus session. Now you can also use this in your application code to insert the value into a table column. So starting with 12G, your create table, you can specify that one or more columns are identity columns. So when you declare some columns as identity columns, they're internally associated with a sequence which feeds the column. So you can also qualify the identity columns with either the always by default or by default or null keywords. The always keyword specifies that the column value can never be explicitly passed in when you're inserting values into the table, and the value must always be inserted by advancing the sequence. The on default keyword says that the sequence value is only used as a default. So you can always insert values, you can pass in a explicit value in the insert statement, but if you don't pass it in, then it will take the sequence value. And the by default on null is very similar to by default, with the one exception being that if you explicitly pass in a value and it is null, it would then it would take the sequence value. So prior to 12G, the identity syntax wasn't available, and you basically had to go through a slightly more heavy-handed approach by having an insert trigger associated with the table, and then as part of the trigger's action, you would be advancing the sequence. Okay, so the keep attribute is one of the lesser known one amongst users because of the simple reason that in most cases you will not have to use it. It's probably a little more relevant to Java developers, but then again, only in special circumstances. So this is specifically related to application continuity, which is a 12.1 feature. Application continuity aims to give users like a seamless experience when there's an outage. So what it does is it tracks the sessions that are affected by the outage, and instead of throwing timeouts and errors, it tries to replay the workload from the point of failure in such a way that the worst that a user experiences is just a slight delay in execution because they're trying to replay it. So if you're trying to replay a workload that involves a sequence, it's easy to see why you'll have issues because as we've already discussed, the sequence value is never repeated. So by using the keep attribute, this decorates the sequence metadata with certain features so that when you're replaying the keyword, the workload, the same next value will be returned. The default, of course, is no keep, and that's how most of your sequences that you generate are. And unless you explicitly specify keep, you should just assume that the replay is not going to use the same value. Now, the keep attribute is relatively new, and there's a tendency that for it to sometimes be confused with the more well-known shared pool.keep procedure. The shared pool keep procedure is not specific to sequences. It applies to any library cache object. The goal is that if you specify keep, it prevents the object from aging out. So, of course, we can use this with any hot sequence objects that's used a lot. Sometimes, even if it's not a hot sequence object, you might have an wrongly sized shared pool. At other times, you might have the right shared pool size, but you might have a very busy workload. So lots of hot objects that causes the sequence to get aged out. Okay. The sequence cache is possibly the most important attribute of an Oracle sequence. So the cache essentially caches a block of sequence values in memory to avoid having to make a trip to disk in order to get each next value. So by default, all sequences are cached, and they're associated with a default cache size of 20. So this means that if an instance, every time an instance gets values from the disk, it gets them in blocks of 20, and sessions on that same instance pick off the values in this cache. So this is basically, like I said, a mechanism to reduce the number of trips you make to disk. And the cache is instance local. So if you have a number of instances in a rack setting, then each one has a different block of numbers cached in the rest tree. This is again where you can see the perceived gaps. So it's easy to see why it almost makes no sense to have an uncached sequence, because even if you intend to use the sequence very rarely, there's no rational reason why you'd want to go to disk for every next val. Especially given that the default cache size is so small, it's just 20. So one downside, though, to caching is how you recover from caches. Because the cache is stored in memory in the SGA, if the instance goes down, you lose the cache numbers. And besides, there's no way to see how many numbers in the cache were used or unused. So you basically simply have to throw out the entire cache and you read a completely new cache of values from disk. And this is essentially the most important trade-off associated with sequence objects, picking the right cache size. Because you want to make sure that it's large enough that your workload is performant, but at the same time, you don't want to make it so large that you lose a huge chunk of values every time there's a failure. So over the years, we've seen numerous parallel workloads that use sequences to populate a table. And whenever it's a heavy workload, pretty much every time we've required altering the cache size from 20. So the takeaway is that the default of 20 is fairly small if you have a reasonable sized workload. Okay. By default, sequences are unordered. What we mean by this is that there is no enforcement on the order in which next vals are given out if you have two sessions that are, advancing the sequence in parallel. An ordered sequence is declared by specifying the order attribute during creation. And if you have an ordered sequence, there's a strict ordering across sessions that access the sequence. So that means if session 1 advances the sequence before session 2, then session 1 should see a value that occurs earlier in the sequence space. Now, in a non-rack setting, when you have a single instance, ordered and unordered sequences are pretty much indistinguishable, because as we discussed, the sequence cache is instance local. So sessions are always going to pick from the sequence cache in order. They're going to use some form of lock to protect concurrent access. And the true issue only occurs when an ordered sequence is accessed on rack. This is because you have to maintain ordering across sessions and across instances. And you need to get a DLM lock for maintaining ordering for every next val. And if this turns out to be a hot sequence, then this can be a big performance issue, as we've seen with some customers. So in general, the idea is that we discourage using ordered sequences on rack. And so far, that's the first line of defense that we go to if someone's facing performance issues on rack with an ordered sequence. And this has generally worked with most customers. They understand that, you'll always have to get a lock. And so most customers have been okay with using an unordered sequence. However, in the recent past, we've had a few cases where customers have been using ordered sequences for a while for historic reasons, and they weren't prepared to make the move to unordered. So this is again, despite the fact, as I already mentioned in the earlier slides, that true ordering at the commit level is not guaranteed, even by an ordered sequence. So we've been actively working on a few ideas to address performance for ordered sequences, and I'll be discussing some of these ideas in the coming slides. So the last point about ordered sequences is that they're almost always cached. Now, this seems a little counterintuitive because caches, as I discussed, are instance local. And if every next val must be synchronized across instances, it seems like having a cache should not provide any additional benefit. But in reality, it does, especially when you have sequences whose access is skewed towards one instance. So basically, we'll look at it in the next 1 or 2 slides to see how caches are instance local, but when you are accessing them on rack, you find a way to logically share these caches. Okay. So there are three primary points of synchronization with sequence access, and almost all of them, like I said, have to deal with cached and ordered sequences. So since we just looked at caching and ordering, let's see which parts of the sequence access each of these synchronization constructs protect. So the first point of synchronization is related purely to cache sequences, has nothing to do with order. This is the sequence latch. And if you're ever looking at an AWR report where sequence has contention, and you should see this as KDN LCH on the AWR report. So this latch protects access to the instance local cache. So you have a separate latch for each instance. Now, second point of synchronization is the SQNQ, which is used for replenishing the cache. So this is essentially once you've exhausted the cache on an instance, you're going to make a trip to disk to get the next cache of values. So you can also view this as protecting DC sequences, which is the sequence row cache object. On the AWR report, you should see this as the SQNQ. Now, the bulk of the issues, so the first two are again related specifically to cache sequences. And the bulk of the issues seen with sequences usually has to do with massive parallel inserts where we're contending on the SQNQ when you're replenishing the cache. Of course, this contention is pronounced on rack because we now have to go through the DLM even for the SQNQ, and this is expensive. So the recommendation we have generally, or at least that we've had so far for SQNQ contention with customers, is increasing the cache size. That's like, very easy to see that if you have a larger cache size, then you're going to go less to disk. Other suggestions have included, trying to reduce the number of hard passes, invalidations in the SGA, etc. So usually that recommendation brings down the problem to some acceptable level, and then life goes on for some time, and then we'll have to deal with it all over again because someone else is facing the same issue. Now, the final point of synchronization is specific to ordered sequences. So the ordered sequence NQ is the SVNQ, and this is how you would see it on the AWR report as well. So it's an instance lock, and ordering is enforced by getting this lock and writing the next val that must be given out to the NQ's lock value. So this is almost always a source of contention because, like I said, you have to get it for every next val. And when you're on rack, this gets expensive very quickly. So like I also already said, we don't suggest using ordered sequences on rack. And our first suggestion is always to alter the sequence so it's not ordered. We've also suggested increasing the cache size because sometimes, despite seeing SV contention, the underlying cause could be SQ. Because you always have to get the SV for an ordered sequence before you go to disk to replenish the cache. So even if you have an SQ problem, it can sometimes show up as SV. Okay, so in the next few slides, we will be introducing a cache resizing feature that automatically adjusts this cache size. Okay, so this slide talks about some recent performance bottlenecks that we address with customers. So while these are specific to some customers, I'd like to point out that most performance issues that we see with sequences usually follow one of the same patterns. So in the first case, we had someone moving from a non-rack to a rack setup. So they had a 2-node rack setup in active passive mode. They did use an ordered sequence, but it was primarily used on one instance. And the issue showed up as contention on SV. And this was one of those examples where the underlying issue was actually with SQ. Then, as was customary, we got them to increase the cache size. We also requested that they make the sequence unordered. And they did all of this. And it brought down the wait time partially, but it was still not within the performance timeline that they were interested in. So this required a closer look since we had finished our arsenal of recommendations that we usually had. The second case, again, we had a 2-node setup. And in this case, the customer was moving from on-premise to cloud. What was interesting about this case is that they were unable to get rid of their ordered sequence. Their application had been using this for a long time, and they didn't want to make a change at this point. So at this point, we realized that we had to specifically address the ordered sequence contention. So before we actually discuss the changes that were made, I'm going to give you a quick look at how these NQs come into play. Okay, so let's start first with unordered sequences. Now, every sequence object has its metadata in one row of sequence dollar. This is protected by DC sequences, the row cache object DC sequences. The high watermark column that you see there is the start of the next block of sequence numbers that you can pick up from disk. So in this example, we have two instances. Every instance has its own instance local sequence cache. Instance 1 is working with the sequence numbers 1 to 20. Instance 2 is working with sequence 1 numbers 21 to 40. They each have their own latch to serialize access to their local cache. Now, this latch is usually held for a very short period of time because most of the work done under the latch is simply to read a sequence number and then basically advance to the next value. So this is why you typically don't see the latch showing up in your AWR report, and it's usually the other two NQs that show up. Now, if a session gets the latch and sees that the cache is exhausted, as is the case with instance 2, so it gets the latch, it sees that it's at 40, which is the end of the cache, then it tries to acquire the SQNQ because now it needs to replenish the cache. And once the cache is refreshed with a new set of values, in this case, it's range 60 to 80, sessions can continue reading values of the cache by using the lock. Okay. With ordered sequences, as previously discussed, we have one additional lock, which is the SVNQ. Every instance first acquires this SVNQ in null mode once the sequence is loaded, and it is held in the background by the LCK0 process. Once again, let's look at the example with two instances. Instance 2 is working with a cache of values 1 to 20, and instance 1 is using values 40 to 60. Now, when a foreground or session wants to advance the sequence, it first gets the it first gets the SVNQ in exclusive mode, and it writes the next val, which is in this case 44, into the lock value. So it basically session 3 in this case writes 44 as the next val. Now, when instance 2 acquires this lock, because instance 2 is working with a cache of 1 to 20, it sees that the next val is beyond its cache. So instead of going to disk, it basically just adjusts its cache ends so that the next val that it sees falls within the cache boundaries. So it basically just adjusts the cache to 41 to 60. So in a sense, it's logically sharing the cache of instance 1. Okay. So the first topic we'll go over to address sequence performance is dynamic cache resizing. This specifically addresses contention on the SQNQ. So this is planned for the next release. So you should see it whenever 21 is out. So as the name suggests, the idea is to elastically grow and shrink the sequence cache based on usage. So this is basically going to eliminate the need for users having to manually alter the sequence cache size through a DDL whenever they see contention. So basically, users can continue to stick to their default cache size of 20, and the elastic nature of the cache will automatically take care of bringing down contention on the NQ. So let's first look at how this works for unordered sequences. So what we do is we see how much time has passed since the last cache replenishment, and we see what the cache size was at that time. And we use both these parameters to project how many sequence values will be consumed in the next 10 seconds. So, and we believe that this 10 seconds is small enough that the cache size is not going to go indefinitely. So once we determine how many sequence values might be used in the next 10 seconds, we basically set our dynamic cache size to that. So you can easily see that if your sequence usage goes down, the cache size would go down. If the sequence use goes up, it would go up. But in order to, so we have certain limits in place. One is that it will never fall below what the user has specified as the static cache size in the DDL. So for example, if you're using the default size of 20, it would never fall below 20. And we also don't allow it to grow massively with each step. So we limit the increment to 10x the previous cache size, and we don't let it grow beyond 1 million. Also, this dynamic cache size is not persisted to disk. On disk, you would still have what the user specified with the DDL. So no DDL changes are required to get a benefit from this feature. So this is how we evaluated the feature. The bottom left table shows the throughput that we measured by manually, this is without the feature, this is by manually configuring the sequence cache sizes from 2 to, by factors of 10. And we saw that, and then when we turned on the feature and we worked with a default cache size of 20, we saw that the feature automatically gave us the best throughput that you could get from manually configured cache sizes. So we got around 1.5 million inserts per second. And when we checked the cache size, it had grown to around 25K, which was the cache size at which we got the best performance even when we manually configured it. Okay. So this dynamic cache resizing was for ordered sequences was not very straightforward to implement. This is because, like as we discussed, the cache is instance local. So if every instance is resizing its cache locally, then every instance can end up with a completely different cache size. And as we've also seen that we discussed how on rack instances logically share the caches by adjusting the boundaries. So now if every instance has a completely different cache size, this adjustment algorithm stops working. So to overcome this, in addition to the next val that is put in the SVNQ, we also put in the high watermark along with the next val. So this required some changes to use a variable size lock. Now instances can read the next val as they always do. In addition, they also read the high watermark, and the adjustment algorithm also becomes a lot simpler. You just use the next val and the high watermark as cache boundaries, as you can see in this example here. So you read the next val as 58, you see the high watermark as 70. So even though your original cache was 1 to 52, you basically just adjust. You use the F58 as the next val and you adjust the cache from there to 70. So once again, we evaluated how ordered sequences perform by comparing it with the manually configured cache sizes. So with the manually configured cache sizes in the table that you see here, you can see that the wait time stagnates somewhere between 2K and 20K cache size. This is because, so this basically means that this feature is not going to give us any benefit beyond that cache size. Because at this point, SQ contention is no longer the issue. We're primarily contending on the ordering NQ or the SV. And there's no way around it because we know that for an ordered sequence, we need to get it for every next wrap. So our cache, the dynamic cache resizing for feature performed about the same as the best that you can get with a manually configured size. But it just shows that this isn't sufficient and we need to tackle the SVNQ contention. Okay, so we've discussed a number of ideas regarding this, and hopefully this will be there soon with no guarantees. So if all things go well, we hope to have some interesting solution for bringing down SV. We're working on this actively. So hopefully it'll be some combination of having prioritizing local waiters. This helps with the active passive model where you have the sequence mostly being used on one instance. Deferred ping is a popular buffer cache algorithm. We planned trying to do something similar here, where the instance continues to hold the SVNQ and only releases when it's actually pinged by another instance. So it's a little similar to the first point of prioritizing local waiters. We've also discussed ideas where one of the session that gets the lock reserves more sequence values and then distributes them among the waiters according to their waiter IDs, things like that. So that's what we have planned for the future. Okay, now let's look at another fairly recent feature. This is available since 18C called Scalable Sequences. This helps to address a different type of contention that's not directly tied to the internals of the sequence NQs that we looked at so far. Rather, this addresses contention based on how sequences are typically used in applications. So as we've seen before, a very common use case for sequences is to insert the values into a table column and typically with an index on it. Usually this insertion is done with a high degree of parallelism. And since we're inserting growing values from a sequence, the B plus tree grows only at the tail. So this results in a right growing index where the leaf block becomes a hotspot, leading to contention. So previously, we've had a number of techniques to overcome this contention before we implemented scalable sequences. So one way is to have a large cache size. So we know that caches are instance local, so this automatically gives us affinity to instances for the leaf blocks. Another idea that has often been used is to use a reverse key index, where you're basically reversing the bytes of the index. So this helps to spread the heat from one block to multiple cold blocks. A third technique is to use a hash partition index, which helps with the non-rack setup. So unfortunately, all of these techniques come with some limitations. Now, a large cache size, while it helps to to affinitize blocks to the instances, it does not help in a non-rack setting where you have a single instance. With the reverse key index, yes, we are exchanging one hot block for multiple cold blocks, but this increases the number of physical reads we're doing of these cold blocks, because so this means we're reading more number of blocks for the same number of inserts in the workload. Finally, the hash partition index is only useful in a single instance setting, so it's not going to give us instance level affinity. So what is our ideal solution? What we'd like is a solution that works for both single as well as rack instances. That is, we want leaf blocks to be affinitized to instances, and we also want it to be affinitized to processors in a non-rack setting. And we want all of this without application changes or having to add a new index or a reverse index or altering an existing index, etc. So this is the solution that we have in place today. So the sequence value is prefixed with a 6-digit numeric offset. This is derived as follows. The first 3 digits is an instance offset, and it's computed as the instance ID modulo 100, and then we add 100. I'll explain why we need to add that 100 shortly. The session offset is the session ID modulo 1000. That's the next 3 digits. Now, the most significant digit has to be 1, and we need this in order to prevent duplicates. And this is best understood by looking at an example. So let's say we're looking at 2 different offsets generated for the same instance. So even on this issue can occur even on the same instance. So let's say the instance offset is 0, and you have 2 different sessions with session offsets 0 and 100. So let's say the first session returns a next val of 12. So the prefix is going to, assuming we don't have the leading 1, the prefix is going to be 100. At some later point, the second session may end up returning a next value of 10012. Now this had a session prefix of 0. So without the leading 1, you can see that these sequence values are identical, and this basically violates the sequence property of returning unique values. Okay. Now, scalable sequences can be defined in 2 flavors with the extend and the NOEXTEND keywords. The default is NOEXTEND. So let's look at that first. With a NOEXTEND scale sequence, all generated values have the same number of digits as the maximum digits in either min-val or max-val. So this is intuitive. It just means that the numeric scale prefix uses 6 digits from the existing sequence space. And this is an extremely important mode, and that's why it's the default, because it ensures backward compatibility. Just by making a sequence scalable, you don't want to go beyond the sequence space, because applications that are consuming it may not be written or ready to accept such wide values. So as an example, if a sequence has a max value of say 1 million, which is 7 digits, since we're using up 6 digits for the instance and session offsets, then you can only get values 1 to 9. And this is assuming that you are on a rack setting. If you weren't in a rack setting, then you can use the instance offset digits as well as part of the sequence. The second property is the extend mode. This is the counterpart of the NOEXTEND. And as the name suggests, the mode will not use the existing sequence value space for the prefix. Instead, the generated sequence values will be 6 digits wider than the number of digits in min-val or max-val. So this is more useful if you don't want to, eat up your sequence space, and it's more useful if you have a new application that's not going to break from widening the sequence. Okay, the syntax is straightforward. It just involves two keywords, scale and extend. Um, the extend keyword is optional, and by default, scale sequences are no extend, just for backward compatibility. One important point to note here is that if a scalable sequence has returned any values at all, any scaled values, and you then alter it to no scale, then we immediately update the high watermark on disk with the next value of with the next value and the largest possible scale prefix. So we absolutely have to do this to avoid duplicates, especially with the no extend clause, because if you're, once you alter it to no scale, it starts generating values without the scale prefix. But at some point, the sequence value can grow to a value where it produces one with the same prefix that you had returned earlier, which basically breaks the uniqueness. So it's understandable why we don't recommend using scalable sequences with ordered sequences, because you are losing ordering as soon as you prefix the 6 digits. So you are not getting ordering, but you're also paying the cost of getting the extra NQ for the ordered sequence. Okay. How do sequences work on ADG? Oracle Active Data Guard, it basically provides read-only access to a physical standby while redo is active, while redo applies active. And if a sequence is accessed on the standby, we need to ensure that it is coherent with both the definition and its use on the primary. Of course, we know that we can't update the sequence high watermark on disk for the standby because it's read-only, but can we at least read and use this high watermark? It turns out that we can't easily do so without synchronizing on the redo application, because we don't know what was the last cache size that not the cache size, what's the last cache of values that the primary used. To get around this, the standby always obtains a cache of values by making a remote connection to the primary. So once again, optimal sizing of the cache is key here, because you don't want to make too many remote calls to the primary. Okay. A small note on using sequences with parallel DML. So this is just an additional feature that's part of the sequence implementation. That you can update a table column with a sequence using the enable parallel DML hint, and you can specify a certain DOP. So this automatically divides the sequence cache between the specified number of PQ workers, and the speed up is achieved on two accounts. One is, of course, just from using 3 parallel workers. The second is that every parallel worker maintains its own local worker cache. So since they have their own local worker cache and they basically pick values from the instance cache, they eliminate the need to get any kind of lock or latch on the worker cache. And because the SQNQ and the sequence latch are only gotten by the session that initiated the query, so basically the parent. Okay. What are session sequences? Session sequences are defined with the keyword session in the create or alter sequence DDL. Session sequences, as the name suggests, they're local to the session. So every new session will begin returning values from the beginning of the sequence space. That is from the sequence min val. So you can view this as a form of automatically restarting of the sequence in every session. So the good thing about a session sequence is that you never have to make a trip to disk for next vals, because we never have to load a new cache of values. By default, sequences are not session sequences. So if you just create a sequence, create sequence S1, it's not going to be a session sequence. That is what is referred to as a global sequence. You can completely forget about that keyword global right after I say it, because we don't usually use it to refer to regular sequences. You can just refer to it as a regular sequence. So if you want to get a session sequence, you have to explicitly specify the keyword session. Now the restart keyword is used to restart. So this is providing some form of, just like session sequences are kind of having a restart in a session. the restart keyword is used to provide the restart ability in a more generic setting. So that is for regular sequences. So this was introduced in 18C. So when you simply specify restart, the sequence starts from its minimum value. But if you also have the option of specifying a specific integer at which to restart, the only requirement is that this integer must satisfy. I'm only referring to the new ones that were more recently added. The scale and extend flags that we've discussed for scalable sequences are part of this table. All currently used sequences can be monitored with the $V and $GV sequence views. So again, I'm only referring to the columns that were more recently added. Cache size has always been there, and this basically gives you the static cache size of the sequence that was part of the DDL. The new column that's been added is the dynamic cache size. So it basically gives you the current dynamic cache size at a given point in time. As we know that this dynamic cache size can change depending on the usage of the sequence. To trace sequence usage, we use the event shown here, 10290. You can use levels 1 through 5. 1 basically just traces flow. Level 5 goes all the way to dumping everything, including the latch, the lock, the waiters, etc. We almost never encourage turning tracing on in a production system, and especially not for a hot sequence, because the tracing can be extensive even at low trace levels. And when you turn on tracing, it's going to turn on tracing for all sequence objects. And probably not so surprisingly, sequences are used throughout the RDBMS code. So if you just turn this on in a busy system, you should expect to be inundated with traces. Okay, so that's all I had for today. I'm happy to take any questions.
Okay, let me take a look at the questions and see if we have any logged. And we don't have any, guys. So if you have a question, enter it into the YouTube chat now, and I may catch it before we wrap up. So doesn't look like we're getting any questions. This is kind of typical for our yeah, I think that's what we should hope and what we should expect. We tend to, when we have in-person meetings, we tend to have a lot of questions, and somehow that doesn't turn out to be the case.
That's all right. Also, this is, like I said, this is a back to basics talk. So, we've had, I'm sure a lot of this content is familiar. There were a few recent enhancements that I spoke about. So hopefully that is interesting and people would try it out. But otherwise, yeah, I think it should have been easy to follow. So I'm not too surprised that there aren't questions. So
yeah, we've run a few of these streaming sessions, and there's rarely questions. Occasionally there's something. I think this was a very good presentation. I think it covered the basics, and it also gave those that has been playing with this for a long time some insight into some new and exciting features. So I think everyone got something away from this presentation. I think it was very good. So I'll just take one last look at the questions situation, and there are no questions. So at this point, we'll wrap this up. Well, thank you so much for your patience with waiting and for having this presentation for us.
Yeah, thank you for making it happen. I was almost wondering whether we would postpone. So I'm happy that we managed to actually get this done today. Thank you so much.
Very nice. Thank you, and thanks everyone for your patience. Bye for now. See you next time.